Today we're going to take a look at section 7.3. We're going to look at repeating decimals. This is kind of a fun section, and it's very interesting. And when you leave this class today, you're going to be able to wow your friends with a really cool fact that you didn't know coming in. Are you ready for it? It's going to be really exciting. Okay, but we need a little work to get there. So do you remember what we said about when you can write a fraction as a terminating decimal? What was the kicker? Okay, so if the denominator, and it's of the, specifically the reduced fraction, right? Of the reduced fraction. Factors only into 2 and, I should say 2s, you could have multiples of them. 2s and or 5s. That's what we said. Do you guys remember that? We did that back, I think it was in section 7.1. Okay? So what happens if you can't factor it into just 2s and 5s? Well, if that happens, then the fraction will repeat. Not the fraction, the decimal is what I meant to say. The decimal will repeat. Can't spell today. Try it again. The decimal will repeat. So if you change it, it has to be from reduced form. We looked at one where that happened, right? It has to be in reduced form first before you can know for sure. If it's in reduced form and you have a 3 or a factor of 11 or something else like that, right, in the denominator, then that means that you're going to have a repeating decimal. So we're going to do an example of one. This is 1 over 24. How do I know it's in reduced form? There's a 1 on top. There's no way to reduce this and simplify it. And how does 24 factor? What's a factorization for it?
12 and 2.
Okay, 12 and 2. So 2 is prime, so then I need to keep going with 12. What, 12?
2 and 6.
2 and 6. So 2 is prime, so I keep going with 6. And 6 is 2 and 3. So I have a bunch of 2s. All that's good, but the 3 here actually means that it will repeat. Okay, once I hit that 3, I'm going to have a repeating decimal. So how do I show this? Well, this is one of those places where you're going to actually show the division all the way out. Okay, so we're going to take the number 24, and we're going to divide it into the number 1. And of course, it won't go into 1, so we put a decimal point and a 0. And it won't go into 10 either, so we're going to make this 100 now. So the decimal comes straight up. It does not have anything that goes into 10, so there's a 0 there. But then I consider the 24 going into it as though it's the number 100. So how many 24s are there in the number 100? 4. You can kind of think about a quarter being 25. 25 would go in 4 times, so it's going to be slightly more than that. So 4. 4 times 24 is what? 96. And you're welcome to use your calculator to do these multiplications. That's fine. We subtract, we get the number 4. Well, I mean, it doesn't go into 4, which it wouldn't at this point. So we have to put on another 0, and we pull it down. Now we got the number 40. How many 24s are there in 40? Just 1. 1 times 24 is 24, and I subtract, and I get 16. Okay, so still not going to be done. So I go again. Now I have 160. How many 24s are there in 160? 6. If you take your calculator, it'll tell you as well. Like you could literally do 160 divided by 24. The whole number part's what I'm looking for. It's a 6. What is 6 times 24? 144. And what do you get when you subtract here? 16. This is a red flag. It's the same number I had once before. Now, it doesn't necessarily have to be just the step before. Okay, it could be like it was here, but it doesn't have to be. But once you repeat a remainder piece that you've already had before, you're done. And how quickly it is that you repeated it tells you what's repeating. This was just one step back. If I do this again, I'm going to get another 6. and it's going to be a 144. And if I do it again, I'm going to get 16, and then I'm going to get another 6 and a 144. I mean, like, it's going to keep going over and over again. So at this point, this 6 repeats. If you're not sure how many numbers are repeating, because we're going to see some later, just do a few more steps, and it'll very quickly become obvious to you how many of these numbers repeat before we're done repeating. The answer then that we have is 0.0416, but make sure that only the 6 is the repeating part. Okay, so we call this kind of a decimal a repeating decimal. And the repeating block of digits is called the repeat end. Okay, so in our last one, the repeat end was the number 6. And there's a note here that I've already said it out loud, but I'll say it out loud again. I expect to see the division when you do the conversion on these. Because in reality, that is what your students would be doing at this point. They would still be showing the division. So we're going to show it for the sake of that as well for the moment, okay? Okay, so we're going to do another example where we're showing the division. 29 over 99. 29 over 99 is in reduced form. Any idea why I can just say that quickly? Last time it was easy, we had a 1 on top. There's not a 1 on top here. 29 is prime. And 29 actually does not go into 99 perfectly. If you weren't sure, you could actually do 99 divided by 29. You'd very quickly see that it doesn't go in, okay? So this is going to repeat. The other way that you could tell, if you didn't think to do it that way, is you could actually take the 99 and you could divide it down. It is a 9 and an 11. That's 99. 9 and 11 are both prime, and neither 9 nor 11 divides 29. You could try that too if you didn't recognize the 29 being prime. This is another way of thinking about it. So we're going to find a decimal representation. The 29 will be divided by the 99. Clearly does not go in, so we put in a decimal point and a 0. Now 99 will go into 290. How many times? 2. So I'm bringing my decimal up and I'll put a 2. What is 2 times 99? $198. And we will subtract. So what's 290 minus 198? 92?
Wait.
Is it 92?
Yeah.
I think it's 92. Okay. We're going to bring the 0 down. How many times will 99 go into 920? It is 9. What's 9 times 99?
891.
Okay. If we subtract, what do we get? 29. Now, if you notice it at this point, it's the same as the first one. It repeats something we've had previously, 2 steps back actually, right? Because it's 2 steps back, that means there's 2 repeating numbers. But if you aren't sure, just do it a couple more times and you'll very quickly see. If I try this again with the 0, I'm going to have 290, and I'm going to put a 2. And I'm going to get 198, and I'm going to see I have 92. And if I do it again, and I bring down the 0, I'm going to see that I have a 9, right? Just do it until you're convinced or until you can for sure see that the pattern and see what is repeating. In this pattern, the 2 and the 9 repeat. So I have a decimal point, and then I have a 29. Now, it is possible that you actually already knew that 29 over 99's decimal is 0.29. It has a very specific form, and sometimes we recognize these very quickly. If you didn't, it's okay. But it is actually a form that sometimes students will learn somewhere along the way. Hey, if the number is over 9 or 99 or 999, it has this cool little form. So you might have recognized that to go with it. But because it doesn't work for every number all the time, I'd like to show you a little bit more about what's going on here. So what we're going to do next is we're going to take a number that's in repeating form and turn it back into a fraction. Okay? So when this happens, there's a very sort of step-by-step process we can go through that will work all the time. Now, on this one, because the 6 and the 1 have the bar over it, and they're repeating right after the decimal point, I can tell you that the answer is 61 over 99. Okay, it's going to be 61 over 90. It has a very specific form. It's very unique. But if you look at this one, where only the 1's repeating, this isn't going to work on this one. I can't just put the 6 and the 1 over 99 on this problem. So in an effort to show you how it will work for you all the time, we're going to go through it as though we didn't actually have me already tell you that it was going to be 61 over 99, okay? All right, so here's what you're going to do. You're going to set up n equals to 0.61, and you're just going to write it out a couple more times, right? It keeps going, 6, 1, 6, 1, write a few of them out. It doesn't really matter how many, but just so that you can see the pattern, even put a dot, dot, dot if it helps you, whatever, okay? You're going to count how many decimals repeated. How many decimals are repeating in this number? 2. So what we're going to do is we're going to multiply both sides by the number 100. In particular, the reason we're using 100 is because it has 2 zeros, and we had 2 numbers that repeated. So if we had only 1 number that repeats, we'd be multiplying by 10. And if we had 3 numbers that were repeating, we'd be multiplying by 1,000. Okay? That's how we decide what we're multiplying by. In particular, what we want to do is we want to move that decimal point so that the repeat block shifts. And it shifts exactly in the number of places so that things still line up. Because watch what happens when we do this. If I multiply this now, I have 61.6161. And you see the repeating part, 61, is in the same place it was to start with. That's important. If you multiply it by the wrong number of tens, right, like 100 or whatever, if you multiply by the wrong number, they're not going to line up. And you're going to run into a problem, and you're going to know, this isn't working, okay? So they should line up exactly in the same place they were before, because the next step is we're going to eliminate the repeating block. And we're going to do it like this. We're going to subtract from both sides an equivalent value that don't actually have the same form. We're going to subtract the starting value of n. Now, on the left-hand side, that works fine. I mean, 100n minus n is 99n. Cool. But I don't want to subtract n on the right-hand side. There's no n's over there. I want to subtract what n is equal to. And n is equal to, from the very beginning, 0.616161. So on the right-hand side, I'm going to subtract the version that's helpful over here, the 61 version. And when I do that, all of these subtract to give me 0. They all line up perfectly, which leaves me with the number 61. And I can divide by my 99, and lo and behold, just as we talked about before, I have 61 over 99 at the end. Okay? So there's a couple things we remember. One thing that we remember is that we always count how many blocks are repeating. That's how we decide what we multiply by. The second thing that we remember is that we completely subtract n from both sides. It's not just that we're removing the repeating block. That's how it worked out in this problem. But it's going to look a little bit different in the next problem. It's not going to look like just removing the repeating block, although the repeating block will eliminate. It's going to line up perfectly, but there's going to be something else that happens too. So let me show you what happens when we actually don't have all of the values repeat. So the process starts out the same. I write down the 0.61, but I want to write down the repeating values only, right? Just a few more of them. So it's only the one that's repeating this time. Okay? How many numbers repeat? 1. So I'm not going to multiply by 100, even though there's a 6 and a 1 in the value that started. The only value that repeats is one of them, namely the 1. So I'm only going to multiply by 10. Now when I do that, I get the 10n on the left, like I had my 100n before. But the decimal will only shift one location on the right. That will leave me with a 6.1, and then a bunch more 1s after that. Okay? So when I subtract here in a moment, I'm not going to eliminate all the 1s. But I'm going to eliminate the part that keeps repeating indefinitely. Those will line up. But I'm not going to get to the number 6. That's not going to happen here. So when I subtract, again, I subtract n, and I subtract exactly what n is equal to, which is not 0.111. It's 0.61111. Do you see what's happening? Yes, the 0.1 repeating is going to go away, but it's not exactly just that. right? These pieces go away. But I still have 6.1 minus 0.6. That part's different. So 9n on the left. What is 6.1 minus 0.6? Yes, you're right, Kaylee. It's 5.5. Okay, everybody good so far? This looks a little weird. I still have a decimal point. We're going to fix that. But at the moment, we do still have a decimal point. Okay, so we're going to divide both sides by 9. Now, at the moment, this does not look good. In fact, it doesn't even match the directions. The directions said that I want the A and the B on the top, do you see that at the front, to be in integers. And 5.5 is not an integer, right? This is a decimal. It does not satisfy my requirements of the question. So here's what I do. I multiply the top and the bottom by enough that I shift the decimal over to make the 5.5 a whole number. I can do that by shifting it one time, and I do that by multiplying by 10. If I'd had 2 decimal places, right? If it said 5.55, I'd need to multiply by 100. The goal is to create it to be, change it to be a whole number. So this gives me 55 on top. What's going to be on bottom? 90. Now, it is in the fraction form that it's asked for, right? I've got a whole number on the top and the bottom. But it also asks me, or it actually doesn't say it, but what we are going to do is we're going to always make our fractions reduced. This fraction is not reduced. 55 and 90 can both be divided by something. What can they both be divided by? Yeah, 5. So we'll divide by 5 before we're finished. So 55 divided by 5 is 11. 90 divided by 5 is 18. How can you check and make sure that this really is the right answer?
Would be the 11 by the 18?
You can divide the 11 by 18, and you can do it in the calculator, absolutely. So you grab your calculator, and you say 11 divided by 18, and you're looking to see, does it equal 0.61 with the 1 only repeating? And it does. So you can always make sure. You don't need a back of the book at all. Completely irrelevant on these problems. You can do it without it. Okay? All right. Are you ready to be wowed? Because this is my wowing moment. 0.9 repeating. We're going to do the same thing that we did in the last problems, okay? So this is going to be n equals 0.9 repeating. Oh, I'm sorry. So we're going to write out some of these 9s. All right, how many numbers are repeating? 1 number. So what will I multiply by? 10. Good. So I have 10n on the left, and I have 9.999, a bunch of them over here on the right. What's my next step? Subtract n. So on the left, it's minus n. On the right, it's minus, the 0.9 repeating that we started with. Whoops, let me get it lined up. Okay, so as we did before, these 9s are all going to go away. What is 10n minus n on the left? 9n. And what do we have remaining on the right? 9. What's our last step? Divide by 9. What does n equal? 1. This is a proof that 0.9 repeating is equal to 1. That's pretty cool. Because it feels like it's smaller, doesn't it? It feels like it should be smaller. But the infinite nature of 0.9 repeating is that it's equal to the value of 1. Crazy. It's crazy. So go show your friends later. Or don't, but it's still kind of crazy. All right. Couple more things. Okay. If you're looking to find a decimal between 2 values, so the value I chose was 0.9 repeating, just because we had just used it. It's equal to the number 1. But let's pretend for a moment that you didn't know that, or it was something that wasn't quite so obvious, like we just did the problem before and turned it into something else, okay? What would you do? Well, if you're looking for any decimal between them, this number is awfully close to 1 at the very least, right? It's almost 1, even if you didn't know until just a moment ago that it's equal to 1. You're thinking, oh, this is about 1, and this is about 1.1, and it doesn't really look like there's any space in between them. What would you do to find space, to find any value in between them? Well, one thing you could do is you could think about money, right? This is sort of like the idea of the value $1. And this is like the idea of the value $1.10. Money's a good option. What's a number between 1 and 1.1? Any number.
1.5.
1.5. Somebody give me another one.
1.6.
1.6. We can do 1.1. Whoa. Not 1.5. Let's take a step back. I think we missed something. 0.5. That's what I meant to say, I think, too. 1.05, right? $1.05. 1.05, $1.06. And I meant to put here, get that one too, 1.01, $1.01. In particular, over here with the values themselves, whether you think of them as money or not, you can put some zeros on there. So you have 1.0 and you have 1.10. So there's space between them, right? So the numbers 1, 5, and 6 over here are between them. How do we find the number halfway, though? Now, we've already found it. We wrote it. It was one of the ones that was mentioned. Autumn mentioned it as her example. But here's what we would do if we didn't know what to do with that 0.9 repeating, is that you take your calculator and you just do a whole bunch of 0.9s. I don't care how many you do, just do a bunch of them. And the way that we find the halfway point between values, careful there, is that we add them together and we divide by 2. It's called averaging. You guys do it with your grades all the time. If you have 2 equally weighted assignments, think about, like, what is my test average? You'd add the 2 tests together and then you divide by 2, right? That's what we're doing here. The halfway point, or the average, is what we're looking for here. So if you take this and you add a bunch of 9s to the 1.1 and divide by 2, and your calculator is going to eventually give you an expansion that's going to round in a funny way because we didn't really put in the number 1. We put in the number 0.9 repeating-ish. We would get 1.05. Did you? So if you're working with one and it gives you something like this, right? Like maybe it tells you 0.5 repeating. Okay, you just put in 0.5555, a whole bunch of 5s, and the other number it gives you. And you add them together and you divide by 2. All right? It doesn't matter what that number is. The process will work the same way. All right, some addition problems are easier to compute with fractions, and some are easier to compute with decimals. For example, 1/7 plus 5/7 is easier to compute than 0.142857 repeating plus 0.714285 repeating. They're basically telling you that this is the value for this one, and we'll go green. This one is the value for this one, right? Much easier to do 1/7 and 5/7 than it is to do their decimal expansions. But if you did 0.4 and 0.25, that one is easier to do in decimal form than its corresponding fractional form, 2/5 and 1/4. Can you think of situations where it's easier to work with fractions than decimals, and some where it's easier to work with decimals than it is to work with fractions? And these are related questions, just asked in reverse order of one another. So tell me what your thoughts are, and then we'll put them into some kind of a category. Awesome. So fractions are pretty nice to work. If they have like denominators. Can you think of anything else that makes one versus the other easier to work with?
The decimal is terminating.
Yeah, decimals are nice to work with when they terminate. honestly, sometimes things terminate and sometimes have repeating or have denominators that match, and they're equally easy to work with. It just, it's not always an either or. Sometimes both are fine, and sometimes both are bad. Right? It can happen both ways, right? Like 1/3 and 1/7, that's not a good one. They don't have like denominators and they don't terminate. That's no good. It doesn't really matter. Either way you're working with them is not particularly easy. But sometimes it is a very natural choice on this. If you were given these two examples within this problem, it's a very natural choice to pick either the fraction expansion, right, to do it that way, or to pick the decimal one to do it that way. All right, we're going to stop there.